Hello there. In this video, we're going to talk about the call stack. What is the call stack? It's an important data structure inside of your computer that helps your computer call functions inside of code. It's pretty cool. So first off, before you watch this video, you should probably already understand how a stack works, what a stack is in terms of its interface and how to manipulate it with pushes and pops and all that stuff. So see my previous video if you don't understand how to use stacks yet. In this video, I'm just going to talk about the call stack, which is just a special use of the generic stack abstract data structure. Okay, so let's see. First off, let's suppose for the sake of argument that I have, a function called main. This is not a C++ video or a coding video, but the call stack is related to coding, so I'm going to assume you can at least kind of guess what I mean when I write down some code. This is just a simple C++ program. You can imagine that up above main, actually I don't want to use prototypes, but I'm going to put the other functions below. Please forgive me. You can imagine that main calls on the function f, so I'm just going to do a function called f here, and so execution, when it gets to that part of the program on line 3, execution is going to jump down to line 9 to just execute the f function, and then maybe f calls g, and then g, it calls h, and maybe h sometimes calls itself. Maybe we'll say that it's a recursive function. We'll say if, something happens, then we will return a call, or we'll just call h, so it calls itself sometimes. Otherwise, we will have it call on the I function. And then whenever either of those calls return, then, execution just kind of returns to the caller, which would be g in this case. And then we have the I function that just, does whatever, right? So the code here doesn't really matter. What I'm really trying to show you is that one function calls another, and we can sort of allow this to happen under the hood with a call stack. So I'm just going to draw this real fast. Main calls f, and f calls on g, and g calls on h. And h, we'll say for the sake of argument, one time h calls on h, just so it's easier to draw later, and then h eventually calls I for some other reason. Maybe the deeper h calls I, and then eventually this starts to return, right? So if you're a programmer, you kind of take this situation for granted. You think like, well, I just kind of call a function, and then when the function's done, I just return to the place that I'm currently at, and everything is fine. If we had, let's say, local variables in here, they would be preserved. Let's say, I don't know, maybe h is like a number or something like that. Or how about let's do g as a number. We'll say g returns some kind of a number, and then maybe in the f function, when we call g, we'll just print whatever g returned. So g calls h, and then we'll just say like return whatever. Just trying to show you that we might have local variables. So that means in the g function, maybe I'll have a integer a is equal to 5 and integer b is equal to 6. I'm just making up stuff here. And then when we return our data, we might say, return a plus b for whatever reason. This is a nonsense program again. Don't take it too seriously. But I'm just trying to show you that we have functions that can call each other, sometimes call themselves, and maybe they have local variables on top of that. So if you understand what is a stack, then you understand that a stack can hold many different types of data. Just as a quick recap here, a regular generic data structure stack or an abstract data type stack, we could say that the stack held integers. So if I wanted to put like an 8 on there and then put like a 5 on there, it would just kind of stack up as we're adding data. And then when eventually we decided to remove data from the stack, we'd pop it by just removing the thing from the top. But because stacks are supposed to be abstract data types that hold any type of data, we're not limited to putting integers inside of the stack. So we could invent a totally new data structure and put instances of that data structure inside of the stack. For example, if you had a custom class that you wrote yourself and you just called it my class. Let's see, let me do class, my class. And I'll just put braces here. Again, this is not a C++ video, but you can imagine that you sort of made a blueprint for a new type of object and you called it my class, and then later on you're like, let's make instances of my class. let's make an instance called MC1 and MC2 and MC3 and so forth, right? So in the stack, you could just push instances of my class. I'm just going to put MC1 here. If we created MC1 and then pushed it onto the stack, and then we can have MC2 and created an instance of that and just kind of pushed it on the stack. So we can do whatever we want. We can put any type of data on the stack. And this is not exactly the process stack so far. I'm just telling you what a stack in general can do. So now, instead of imagining that we have a custom class called myClass, what if we made a new class called callFrame? I'll say we have like an instance, let's say like a blueprint for a class. We'll call it a callFrame. My penmanship, it's because this pen, I push it down and it always like keeps drawing after I start lifting it up. I don't know what I'm doing wrong. I've been trying this for like 50 videos and it's always bad and wrong. So imagine you have a class called callFrame, and inside of it, you can just put some sort of data inside the callFrame. You can imagine defining what an object might look like and then creating instances and filling it up with data. And then every instance, just like we did with my class, we could just put that onto a stack, right? So now let's try to understand what might be inside a data structure called a callFrame. Because when we have a stack under the hood in our machine that holds instances of callFrames, then we actually have a process stack or a call stack, which allows us to implement these function calls. So let's see. The first thing that we might imagine, I'm going to maybe just do like a little box here, just to let you know that we're deciding what will go inside of a call frame. So this is one call frame. So you can imagine that the f function here, in order for the f function to exist, the particular call to exist, it needs information on what it has, what it is to be alive. It needs its return address. I'm going to put RA here for its return address. What is a return address? Well, when we were inside of the main function, let me draw the execution path real fast. When we were inside of the main function, then execution was going from top to bottom. When we hit this f function call, execution actually jumped to the first line of the f function. Under the hood in assembly, there's a jump instruction that allows you to just kind of jump to a totally different memory location and start executing instructions over there somewhere. In assembly also we have a call instruction, which means I would like to jump to another location, but also I want to remember where I just came from so that it's easy for me to return later. Okay, so we'll call that the return address. The return address in this case would be, let's just call it line 4, meaning when function f returns, then the next instruction that should execute is this return 0. This is C++. It's not really instructions. It's more like statements, but you could just imagine that f gets called, and when it returns, then the next statement is return 0, right? So if we say that the memory location of wherever line 4 starts is the return address of f, then you can imagine that in order for f's, call instance to exist, it has to remember its return address. So therefore, we would put the return address inside of its call frame. So the return address goes in there, and function arguments sometimes go in there. If you know assembly, and that's kind of what we're talking about right now in this video, then you'll know that function arguments, at least the integer arguments, usually come in certain registers like RDI and RSI, or if you're passing float arguments, the first argument would be XMM0 and XMM1 and so forth, right? So you just kind of like load up registers with arguments. But if you have more arguments than you have registers, there's only so many registers you can actually use to pass arguments into a function that you're calling. So what if you run out of float registers, you run out of the general purpose registers, but you want to have more arguments than that? For example, if you look at the ABI, then the integer arguments, there's only 6 registers that we can use to pass integer or pointer arguments. So if you wanted to have 7 arguments or more, then you should be able to do that, but there has to be a different way to accomplish that. So the 7th and beyond arguments will actually show up in the call frame. Oh, I guess RA should probably be blue, because the call frame, I'm just making that green. I'll say return address. So the 7th and beyond arguments, args, we'll just say. So the call frame contains the return address and any argument that's like the 7th argument and beyond. And if you don't have 7 arguments, then that's not going to be in the call frame. It'll just be blank at that point. Sometimes when people are messing around with the stack pointer, they will kind of like save the stack pointer into the RBP register. So basically anytime you push a register in order to preserve it, then it will end up on the call frame, at least at the assembly level. So suppose you're going to use the base pointer register. You probably want to preserve the base pointer before you start using it. So we would push it onto the stack and it would become part of the call frame. Any registers that are designated as Callee-Saved would also be pushed into the call frame, like R12, oh my God, R13, my penmanship. There's like the ones are always L's, okay, and so forth, right? So anything that's designated as a Callee-Saved register that you intend to use would end up getting pushed onto the stack at the assembly level, and thus it would end up in the call frame. But you know, if you aren't going to use any Callee preserved registers, then you don't need to preserve them, and therefore they would not show up in the call frame. And let's see, and local variables. So when you make local variables in assembly, you just basically end up pushing them to the stack. So I'm going to put local variables here. And in a second, I'll show you how that kind of works in higher level languages like on C++. That's why I wrote this down right here, line 12. We're making local variables. And let's see what else. Sure. I should emphasize that local variables are very different from heap variables. But basically, you can imagine now that at some point, let's say that when G was called, let's say execution came in here into main, and then execution jumped into the F function, so it jumped in there, and then F wanted to call on G in order to get some information, right? So we have a call frame just for G, and we have a call frame just for F, and we have a call frame just for main. And so we have like 3 items on our stack at least, just to get to that point of the program. And every call frame, you know, basically has this sort of information inside of it. The return address, so the function knows where to jump back to when it's time to return from the function. 7th and beyond arguments, if any exist. The base pointer, if you happen to modify that at the assembly level. And then same thing for Callee-Saved registers, and then local variables, which you could probably imagine more clearly. So now I'm just going to erase this call frame thing here. Oh God, this eraser needs to be improved. Oh my gosh, maybe I should make that bigger. I need like a little shortcut to make it bigger for a second, because I don't really want to draw that thing on top again. That's just annoying. I don't want to do it. I won't do it. I won't do it. Okay, so imagine now that we are trying to sort of trace what's happening in our call graph, you know, in our program while we're calling functions. So first, imagine we have an empty stack. And again, if you don't understand stacks, you better go see my other video. Imagine we have an empty stack. The stack is not ever really going to be empty when you launch your program. It's going to be there's going to be stuff on it already. But let's just pretend that we haven't put anything on the stack at this point. So there would be you know, a call frame just for the main function. I'm just going to write main here to say that this is the call frame for main. So it contains all the information that main needs. And if you have a main function in the first place, then you're probably linking against the GCC libraries, which means main definitely has to return somewhere inside of the GCC library. So this kind of makes sense for our program. So it's a call frame for main. And then when main calls on F, then another call frame gets created for F. And then when F calls on G, another call frame gets created for G. I don't know if I need to put these parentheses, but I guess I've already started to do that. And then G calls H. And then H sometimes calls itself. So I'm going to put another call frame for H up here. Oh my God. H's look like just crazy. Okay, that's better. Every time I lift up the pen. H calls itself. Sometimes we'll just say that it calls itself once in this case, and then H calls I, and then let's just say that's the end of our little call graph. When I is finished doing whatever it's going to do, then it'll just return to the caller, right? So notice how every single time we made a function call, we added a call frame for that particular instance of a call, and we called it a call frame. Something else that I should point out is that I have been describing to you a call frame as if it's a data structure with sort of like a fixed amount of data inside of it. and you would sort of blob that whole block of data on at the same time. That's not really how it works in assembly. In assembly, you kind of just push, one tiny piece of data at a time, but in the abstract, you imagine that there's a call frame. Just keep that in mind. Anyway, so in the F function, we've been making these calls F and then G and then H and then H and then I. Eventually, when we got to the, let's say, what did I do wrong? Oh, I did something wrong. I put the local variables in the wrong function. Hang on a second. I want them to be, it would be okay to have them inside of the G function, but I really want them to be inside the H function for a certain reason. So I'm just going to cut and paste here. And I'm going to do like local variables inside of the H function and not in the G function. And then G should maybe return an integer result. And then this return statement shouldn't even be in G. It's just going to be inside of H. Just, pretend that I did something with the A and the B variables at some point before returning them. Modify A and B somehow. Maybe I can even put that comment inside of both of the blocks of the if. So like, so maybe if something happens, we'll modify them in one way, and if it doesn't happen, we'll modify them in some other way. And then at the very end, we return them just to kind of feel like we have more of an excuse to have return variables in the first place. And then when H returns something, now we have an excuse to kind of print out whatever H is doing. Okay. And the reason I moved all that inside of H and not in G is because I just want you to know that there are two instances of the H, call instance on the call stack, which means the local variables, they're not linked. They're two distinct copies of each local variable inside of the stack. Think of it this way. When we call our H the first time, we have an integer A and an integer B. You could imagine that there's an integer A and an integer B sitting inside of the call frame somewhere, being pushed onto the call stack. But the other called H also has a variable A and a variable B. But because those are local variables, changing one doesn't actually modify the other copy that is in the other call frame. So you could imagine this as A sub 1 and B sub 1, and then A sub 2 and B sub 2. This is kind of important later on when you realize that your operating system is capable of launching multiple threads for your program, and local variables won't potentially become race conditions, which is just like for a totally different video. But for now, just understand these are totally separate instances. If I change A sub 2, it's not changing A sub 1 and vice versa. And same thing for B. So anyway, we make all these calls, and somewhere along the way, we're creating a bunch of data and a bunch of call frames. Eventually, when we are done with the I function, when I wants to return, here we don't have an explicit return statement, but if you know C++ or higher level languages, if there's no return statement in most of these languages, for a void function, it just returns when it reaches the end of the function. We don't really need to say return because it doesn't return anything, it just ends. So when I is ready to return, what happens is we look inside of its call frame and we look for the return address, which is inside of its call frame. The return address specifies exactly where we're supposed to return. For example, maybe we're supposed to return right here. Maybe we're supposed to return right here. Maybe to make things a little bit more interesting, let's put like a little code right after those 2 points. So maybe if we called H, then we increased A, and if not, then we increased B, something like that. So that means the call frame for the first H function, let's see, if it called itself, then that means this block right here is the first part of the if block. So the return address for H, return address, would actually be pointing to the next line, right? So when H called on H, it would look at line 21 or whatever the address was for that instruction to begin at increasing A, and it would just say that's the return address, so that whenever H returns from itself, it ends up executing A++, and then the same thing for I. So going back on I has a return address, so when we're inside of the I function, it's got its own call frame and it knows where it's supposed to return, which in this case would be that instruction right there, or that statement right there. So whatever is the first instruction that implements that higher level language statement, that's going to be the return address inside the I call frame. So we look inside of the call frame for the return address. We know where to return. It's going to return to H at this point in time. And once we're done with that, then we just deallocate the call frame. In assembly language, all we're really doing is moving the stack pointer and just sort of ignoring the call frame from that point forward, and we'll call it junk data. So the data is kind of actually still there, but we're just not using it. And then later, if we want to start adding more stuff on top of the stack, then it will just overwrite that junk data. But for now, just imagine that it's gone. Anyway, so then we return from I back to H. And so that's line 26 right here. Imagine we perform this instruction, the B++, and then execution falls through down to the very end, the return statement. So then same thing happens. This version, or I guess this version of H had its own, no, hang on a second. We returned from I. This version of H knew that it was supposed to return to H. So that means execution will basically jump from here to right here. So it kind of jumps, back to that next line like we talked about before. When it returns, based off the return address, then again, you can imagine that that call frame is deallocated or just ignored as junk data, and the top of the stack is kind of like moving. And then when that call on H finishes, so, when A++ gets executed and then execution falls through down to the return statement, then again, H has its own return address in its call frame, or that instance of H has its own call frame. Then it knows where to return, and this time it knows to return to whoever called H in the very first place. So it's going to be, I guess it's going to be like when it returns, it's going to go back to G. There's nothing after the cout H on G, but I guess you could imagine under the hood, instead of like another statement, you can imagine more stuff is happening, right? Like when we called H, and then we returned, then we had an expression that evaluated to something because H returned a value, and then we would send that to the stream operator. So in assembly, there are many instructions happening after the call to H, but you could just imagine at this point, it's just going to finish up that existing statement and then move down to finish and return. So then again, we just returned from H to G. So we deallocated that call frame. The top of the stack is now somewhere around there in that call frame. When G finishes and it returns, same thing. It's got a return address, so it knows where to return. And then top of the stack kind of goes down there, and G knows to jump to whoever called it because of the return address. So it's going to be at this point in time. Again, there's more statements that happen after the return because there's a cout and a stream operator, But, basically when F is done, then again, it's going to use the return address and know where to jump back to, which is just going to be this next line right here. So when F was called originally, it like ended up calling H, and then H, called itself, and H called itself again, and then it called I, and then we returned from I, and then we returned from H, and returned from H twice, and then eventually we returned to G, and then we returned to F. Finally, after F and all of its calls were finished, then execution returned just to line 4, and that's basically saying like, oh, what happens when F is done? Let's look at its return address, pop that off the call stack, and then the top of the stack is basically just sitting inside of the main function. So yeah, this is how we implement function calls in the machine. There's really no, if you think about it, from a certain point of view, there's no such thing as functions inside the machine. In assembly language, we certainly see that we have a label, and then we have like a return instruction, we have a call instruction, but there's no like function. It's all just ones and zeros all over the place, right? So the idea of labels and functions and things, that's kind of an abstraction just for the human being with feelings to make it a little bit easier for us to program. So this is how we implement it with a call stack. We have a stack, and we stack things on top of the stack. And the things that we stack are called call frames. Call frames are kind of flexible because sometimes there's more data, sometimes there's less data depending on what the function itself is doing. But it allows us to have a function call itself many times. It allows us to have many different instances of function calls exist at the same time, even if we're only looking at the very top of the call stack in terms of execution, and have all the local variables not conflict with each other. And then, like we have a trail of breadcrumbs when we start returning and returning and returning. The stack makes it really, really easy. And so, in the abstract, we can basically say that there are functions in our machines because this implementation helps make it happen. One last thing that I wanted to say before I go here is just keep in mind that these local variables, they're on the stack, but dynamically allocated memory is not on the stack. Let me just show you what I'm talking about right here. You probably understand the heap already at this point. If you're watching this video, then you know a little bit about dynamic memory allocation. So I'm just going to do, let's say we have like a f function, void f. And inside of the f function, we have, let's say, an integer pointer p. And we will allocate p to a new instance of an integer. And maybe there's another integer a and an integer b. So just so you know, the variables a and b and also p, they're considered local variables because I just declared them. I declared a pointer on line 4. I declared 2 integers on line 7. Maybe I should put those like at the top, I guess. Okay, so lines 4 and 5, they declare local variables. The pointer is a special type of variable, right, that just points to a memory location. So the thing that it points to might not be a local variable, but the pointer itself is a local variable. So these 3 variables on lines 4 and 5, a and b and p, those are on the stack. Any local variable gets put on the stack. And then when you allocate a new integer with dynamic memory, maybe you could imagine if you're a C programmer, this would be a call to malloc rather than new. Then what's happening under the hood is that the system goes and tries to find some free memory in a different area of your process called the heap, not the stack. It tries to find some free memory in the heap. Once it finds some, then it designates that as being in use, and then it returns to you the memory location of that new allocation. So in this case, we're allocating a new integer, so that's going to be 32 bits of data or 4 bytes. And so it just finds 4 bytes somewhere in the heap, and it finds the memory location of the very first byte, and it returns that to the caller. And so p, its value is now going to be the memory location of the new integer that you allocated. But p itself is on the stack. So p is kind of weird, right? Like p exists on the stack, but it points to something in the heap. Keep in mind the difference. And then if we just let this function go to the very end without cleaning up that memory, we would have a memory leak. I should probably just do like a dedicated video on pointers for people who are interested in pointers in higher level languages later. But keep in mind that when the function ends and you pop the call frame off the call stack, then that automatically cleans up all the local variables. So a and b and p itself will be deallocated and not become memory leaks. However, the thing that p pointed to, that will be a memory leak. I guess that's a topic that's too advanced for this stack video. But I just want you to know the difference between something that exists on the stack and something that exists on the heap. Okay, so then I think the last thing that I need to show you here is let me let's see. Assembler. Okay, so here's my favorite book. I love to pump up this book. It's awesome. The author is like a brilliant man, very kind man. He offers this book for free. It's got a copyleft license. You can literally just download it for free on his website, or just get it from a friend, and it's legal because this is an open book, basically. It's called x86-64 Assembly Language Programming with Ubuntu by the brilliant Dr. Ed Jorgensen, PhD, or Professor Ed Jorgensen. This is the latest version that I'm working with right now. I think it's the latest version. I don't know. He updates this thing all the time. It's always getting better. But if we look at this book, you can get a copy of it on your own, or you can just watch this video. I'm going to go to section 12.8.3. So section 12, 12.8, 12.8.3, called the call frame. And here you can kind of see a description of some of the stuff that I talked about in terms of what sort of data you would expect to see in the call frame. But if you just kind of look down a little bit, you can see that we are sort of pushing some preserved registers into the call frame, and we'll sort of like save the stack pointer as the RBP register. But before we do that, we want to push the RBP register, and then notice how here it shows that there's a return address, and the RIP register, that's actually the instruction pointer register. The stack pointer is RSP, and then other arguments that go into it. So just keep in mind that we have a little layout here, and then somewhere else there was something I wanted to show you here. No. Nope. Okay, I guess I'm gonna... Oh, I guess I was just supposed to show you the call frame anyway. Okay, so I guess that's pretty much it. I just wanted to show you some extra stuff, just so you understand this is the basic idea of the stack frame layout. And oh, okay, I found it. I spent a second scrolling through the book to find the other diagram that I really wanted to show you. So same book, x86-64 assembly with Ubuntu, by Ed Jorgensen, Professor Ed Jorgensen, PhD. And if you look at section 9.3, there's another picture here that's kind of useful. And it basically shows, you know, the general idea of how information is laid out inside of your process. So when you launch a process in order to execute your program, then it's kind of laid out like this. There's like a little reserved area. And then there is the text section. For assembly, you know, that's where you have all your instructions. And then there's the data section. And then there's uninitialized data, which is the BSS section if we're talking about YASM assembly. And then notice how in this big blob of an area right here, we have the heap and the stack kind of sharing an area inside of available memory. It's important to understand that the stack, when you actually add things onto the process stack, like call frame data, you're actually decreasing memory locations. So the stack grows downward in memory. So I think I'm going to put this in another video, but basically right now I just want to show you if we have memory location. Let's pretend that we have like a stack here and there's like a couple of frames, you know, sitting on top of it. Suppose you had, I don't know, memory location OX, 99 or something. Suppose for the sake of argument, we're only pushing 1 byte at a time, so it's easier for me to write. Then that means, you know, the next thing that shows up, you know, a little higher on the stack, you would intuitively think that the memory location is 100 instead of 99, right? Or if this is hex, then I guess I increase that 9 to A. But it actually goes down in memory. So, I mean, look at this diagram right here. The stack goes down in memory. So every time you push to the stack, you're pushing to a lower and lower and lower memory location. So right here, I'm just going to write down OX98, and it just keeps going down and down and down. Let's see, 1, 2, 3, 4, 5, right? And the heap is something that grows upward in memory. So the heap, when you call new allocations, like if you say new or malloc or, you know, some kind of dynamic memory, then its memory locations grow up and the stack grows down. And if they ever actually meet, then you've ran out of memory. Just keep that in mind. But, you know, in modern systems, the heap can kind of grow almost endlessly. I'm sure you've all been running programs in the past and noticed that the program was consuming gigabytes of data, right? But it's not like you had gigabytes of data allocated to that process when you first opened it up. Like if you have a browser with like 100 million tabs open, I know some of you people do that. Then when you first open your browser, it doesn't really use that much memory. But then as you start opening more tabs, maybe some pages are doing some weird stuff and you get memory leaks, then the heap starts to grow and grow and grow. And then you'll notice the process takes way more than it did in the beginning. So the heap can kind of grow in an unbounded way. Of course, that is limited to your physical system RAM. And eventually in the far off future, we'll be limited by whatever 64 bits can get us. I don't think we're ever going to reach that in my lifetime, but I've been wrong many times before. However, the stack, it grows downward in memory and it's kind of limited. You can actually overflow your stack pretty easily. So when the stack grows downward too much, then you have a stack overflow and the program crashes. But when the heap grows, then it can just be resized again and again and again, or that little block can kind of expand again and again and again. If you don't believe me, try writing a program with a recursive loop that just goes on forever. So imagine, actually, I don't know, don't do this on your boss's computer, because maybe it'll crash things. Do it on your own personal computer. But imagine we have like a function f, and you know, you'll probably want to call f inside of main or something. So I'll just say like int main, and we'll just call f right away, and then return 0. When you're inside of f, you just call f, right? So this is like a horrible program. If you ran this, very quickly you'd crash the program, because every single time you call f, you're adding another call frame on top of the stack. Your call stack is going to just be filled with f call frames, and then, you know, it runs out of available memory locations to use, and then you're just done. It just crashes the whole program. So let's see. I think hopefully now you feel like you're an expert on the process stack and call frames. Thank you for watching this video, and I hope you learned a little bit and had some fun. I guess I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website, where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.